Yeah, there we go. Now I can hear myself even. Okay, so thank you very much for the kind introduction, and I'd also like to thank the organizers for inviting me. I'd like to congratulate all of you on the renewal of your amazing center. It's really a pleasure to be here. So I think this is this is the exploratory directions session, I guess. So this is a little bit of a changing gears and changing topics a little bit, but I'll try to make some connections to a lot of the quantum information science we've been hearing about. So yeah, I'm a professor at UC Berkeley, and I want to tell you a little bit about the experiments we do in my group. I'll mention that actually my group is kind of divided into two research directions, and half of the research we do is actually on quantum sensing with color centers in diamond, and we heard two excellent talks about that yesterday from Paola and Viviana. But my talk today is actually going to focus on the other half of my research, so if you want to hear about this, you can invite me back for the next one of these excellent conferences. But so today I'm going to tell you about our efforts to use optical lattice clocks to search for new physics. And given the audience and given the kind of subject of this whole conference, I think it's a fair question to say, why search for new physics at all? What's wrong with all the physics we already have? And do we really want more of it, right? And the answer is that, as good as all the physics is and it lets us do really amazing things, there's some pretty big problems kind of staring us in the face that we don't really know how to solve. And in particular, you're, I'm sure, all aware that actually kind of all the physics that we deal with really is dealing with luminous matter that's actually only something like 5% of the energy in the universe. And the rest of the universe is made up of dark matter, which we know very little about, and dark energy, which we know even less about than dark matter. So that's a problem. It's even more troubling that the 5% of the universe that we know about, we don't actually know why it exists to begin with, because all the physics that we know, there's very little, there's a little bit, but there's very little asymmetry between matter and antimatter that we know about, right? There's very little breaking of charge symmetry. And so we don't understand why there's so much matter in the universe to begin with, even though it's such a small fraction of the total universe. And then the other big problem is we have these excellent theories that we've developed over the past 100 to 120 or so years of quantum mechanics that we all know and love, and also of general relativity. And these are both incredibly successful theories, and yet we don't really know how to combine them. And so we're stuck with this problem where we have these amazing experiments that we can do, and every experiment we do on Earth is consistent with our expectations in the physics that we know about, and yet when we look out at the universe, we understand very little of it. And so that's why we really still need to continue to search for new physics. And then the question is, how do you go about that? And one way to do it is look out at the universe, of course, and we're doing that. Another way is to build bigger and bigger particle accelerators and probe higher and higher energy scales, and we're doing that too. But both of those things are challenging, and we'd really like to find holes in our understanding with experiments that we can do in the lab and on Earth. And I think that the best way to do that we know of now is to keep pushing the precision of these experiments, to make more and more precise experiments in the hopes that we start to see deviations from our expectations, and that gives us some hint of how to understand the physics that we currently don't understand. So with that in mind, I'm going to tell you about trying to use optical atomic clocks to do that. So what is an atomic clock? I'm sure you all know this, but just in case, and so that we're all on the same page, a clock is just a thing that exhibits a periodic oscillation that we can count to keep track of time. And so in your cell phones and laptops and everything, they all have something that looks something like this little quartz tuning fork or something kind of similar. And it just has it's a local oscillator. It has a well-defined, it's a simple harmonic oscillator. It has a well-defined resonance frequency. And so just by counting those oscillations, you can keep track of time. The challenge is that every single one of these that you make will be slightly different from every other one. And then also, it's going to be sensitive to changes in the environment. If the temperature changes, if a piece of dust settles on this thing, those are going to cause these local oscillators to drift around with respect to each other, and we'll very quickly stop agreeing on what time it is. And also, when we're doing physics in the lab, we won't have a good frequency reference with which to kind of compare the measurements that we're making. And so that motivates the idea of an atomic clock. An atomic clock is really kind of the most basic quantum technology you can think of. It takes advantage of the quantized energy levels of atoms, and specifically the idea that every atom has the same, transition energy between the same two electron, states. And so what you can do is you can take your local oscillator, you multiply it up by some factor that you believe you know, and you shine that radiation on your atoms, and you see if they get excited from the ground state to the excited state, And by counting how many atoms get excited, you can feed back and correct for all the imperfections in your local oscillator, all the drifts, all the man-made imperfections, and everything like that. And just by doing that, you all know, because you're quantum scientists, that there's going to be kind of a fundamental limit to how well you can do this, because you're measuring the atoms, you're counting how many of them ended up in G and how many up ended in E, and so there's quantum projection noise associated with that. You're basically doing a quantum coin flip with every one of those measurements, and that immediately tells you how good of a clock you can make. So this sigma here is the fractional frequency uncertainty, but it's also, you can understand it as just how long in seconds it will take your clock to lose 1 second, and then take the inverse of that. So if it takes 10 seconds to lose 1 second, that's not a very good clock, and that's just 10 to the minus 1 fractional frequency uncertainty, right? And so you can see that you can improve this number, make it smaller, just by varying a few parameters here. And there's really not much that you can change. You can change the frequency of your transition. You can change the number of atoms. You can change how long you probe it for and how much dead time you have. And that's really pretty much it. And so following that recipe, people have gotten very good at making these making these atomic clocks, I should say. You can see since they were first invented, they improved by a factor of 10 or so in terms of this fractional frequency uncertainty every 9 years or so. And they've now, with microwave clocks, reached an accuracy and precision at 1 second in 300 million years. So a lot better than the 10 seconds that I gave as my example. And this is really enabling, it's actually changed the world, I would say, because of course it's given us GPS that we all take for granted now. But it's also allowed us to redefine all of the SI units that we know and love in terms of a bunch of fundamental constants, which are just numbers that we've written down, and the hyperfine transition of cesium. So now with this new definition of units, because clocks are the most precise measurement devices that we can make, of anything with units at least, the extent to which you can measure any parameter with units is ultimately determined by how good of a clock you can make. And so that basically motivates making better and better clocks. So as I said, if we look at this equation that we have here that tells us how good our clock can be, there's only so many things you can change. And one of the most obvious things that you can do to improve your clock is to work on this frequency of the transition. And by increasing the number of oscillations per second of your clock, you'll just make a better clock. It's just like adding more ticks on a ruler to make it measure smaller and smaller distances, right, more precisely and accurately. So the obvious thing to do is to move from microwave clocks to optical clocks, move from things that are at tens of gigahertz or gigahertz to tens of gigahertz up into this hundreds of terahertz range. And this is an obvious idea, so you might say, why didn't people do it? And the issue, of course, is that it's very hard to count oscillations of things at hundreds of terahertz. We don't have electronics that can count that fast. And in fact, this wasn't really possible except until the work of some people in this room, including our next speaker, Thomas Udom, and also Ted Hench, in introducing the laser frequency comb, which basically allows us now to count oscillations of light, which is really an amazing thing. And so now you can switch from your local oscillator being this little quartz tuning fork to your local oscillator being a laser, which is just an optical oscillator. And you can move from a hyperfine transition in an alkali atom like cesium or rubidium to an optical transition in a slightly more complicated atom such as alkaline earth atoms like strontium. And so the atoms that we work with in my group and that a number of other groups around the world have chosen to work with are these strontium atoms, and in particular we work with strontium-87. And the reason that we choose this specific element and isotope is it has this beautiful clock transition here that has a 1 millihertz line width for a 400 terahertz transition, which corresponds to a natural quality factor kind of given to us by nature of 10 to the 18. And this is really the thing that we're going to take advantage of to make a very, very good clock. But moving to this narrow optical transition, it comes with some added complications. In particular, because you've increased the frequency, you've also increased the effective Doppler shifts for the same amount of motion and temperature of the atoms. And so you need to do something slightly more complicated than, say, just laser cool the atoms like you would in a microwave atomic fountain or something like that. And so you have to introduce something else. And what we do with these neutral atoms is we trap them in an optical lattice. And as you can see here, what that allows you to do by turning up the confinement along the axial direction of this lattice, so on this, as we move down in terms of these lines here, we're just increasing the depth of this 1D optical lattice, and you can see we go from basically a Doppler broadened line shape to this very narrow clock transition we move into this sideband resolved Lambdicki regime where we've isolated the internal degrees of freedom that we're interested in the clock transition from the external motion of the atoms. And basically the motions become quantized in this lattice. And as a result, now you can take full advantage of this beautiful narrow clock transition, that I already told you about. Of course, that also comes with a price because you're now trapping your atoms. The way that you do that is by taking advantage of the polarizability of the atoms. So when you shine your lattice and trap your atoms inside of it, you're actually shifting the clock levels around, which seems like a terrible thing to do, right? Because we're interested in the energies of this transition. And now, as our atom moves through the lattice, or as our laser changes intensity or something like that, the energy of this clock transition is going to change. But fortunately, again, nature's given us a way around that, which are these kind of happy coincidences where the polarizability of the ground clock state and the polarizability of the excited clock state happen to cross. And these are what are known as magic wavelengths. And by sitting at exactly this crossing here, now these energy levels are indeed still moving around as the atom moves through the lattice or as the lattice changes intensity, but the two energy levels are moving together so that the frequency of the transition is no longer changing. And this is what enables us to make a very good clock, and this is why these are called optical lattice clocks. And now, just since these were first introduced, you can see that they've continued to improve, arguably at an even accelerated rate compared to the rate that microwave atomic clocks were improving before. And we've now reached this sort of astounding number that these clocks are both accurate and precise to better than 1 second in 14 billion years. So if you had two of these clocks ticking side by side from the Big Bang until now, they would agree on the age of the universe to better than 1 second with respect to each other, which is really amazing. And that begs the question, okay, what is this really good for? This is actually better than you need for GPS or something like that. I mean, of course, for unit definitions, you always want to do better. But still, it's most applications of clocks is actually better than you need. What is this good for? And I kind of already told you, what it's really good for is searching for new physics. But I came from a quantum sensing background. I did my PhD in kind of magnetometry with nitrogen vacancy centers and things like that. So initially, my kind of hope when I first started working on these clocks was maybe you can make great sensors out of these clocks. Maybe you can make magnetometers and things like that out of them. And that was a little bit naive for a couple of reasons. The first reason is, of course, smarter people than me who picked these elements and these transitions picked ones that were very insensitive on purpose, because when you're making a clock, you want it to be insensitive to everything, right? This is showing you the systematics table, and we've intentionally picked energy levels that are not sensitive to magnetic fields and things like that. But that's okay. We can pick a slightly different narrow transition and make it sensitive, and then you might think, now it should be a really amazing magnetometer. I can make a magnetometer at this 10 to the minus 18 level performance. And that turns out to also be wrong, because the thing that we're taking advantage of when we make these optical clocks is the fact that we get to count the number of oscillations per second to keep track of time. If you want to measure a magnetic field, instead you're interested in how the energy levels shift when the magnetic field changes, but that doesn't depend on the transition frequency. It just depends on the moment of those levels, right? And so what that means is actually, if you want to take full advantage of this, you need to measure things that actually shift the entire frequency of the transition, that scale with the transition frequency. And so if you want to know what these clocks are good for, I think the best thing to do is to say what scales with the transition frequency. What effects kind of shift the transition frequency around proportional to it. So one obvious thing is just time itself and frequency, because you have cycles per second, and that's what makes these things good for things like navigation, communication, measuring frequency ratios, things like that. But another nice feature is actually that these transitions themselves depend on things like the fine structure constant. And so if the fine structure constant is varying in time or space, then by doing clock comparisons, we can learn about that. Similarly, if there's some kind of dark matter that couples to the electron or to the nucleus and kind of mimics a fine structure constant changing, then we can also learn about that by doing clock comparisons. So this is one thing that these clocks are very good for, and this is one way that we can search for new physics with these clocks. But the last one, and the one that I'll kind of focus on for the rest of my talk, is this idea of Doppler shifts and time dilation also scale with the transition frequency. So it's very natural to kind of use these clocks to, for example, do tests of relativity, and also to do things like maybe gravitational wave detection or tracking of spacecraft using Doppler tracking and things like that. Okay, and so here's my kind of pictorial version of what I'm excited about using these clocks for. And I'm going to zoom in on these two examples that are related, tests of relativity, and then similarly actually using the sensitivity of these clocks to the relativistic effects of gravity to actually map Earth's gravitational potential, which is called geodesy. So the idea here is that there's not very many relativistic effects we can actually be sensitive to, especially not general relativistic effects. And the primary one that we have access to on Earth is this gravitational redshift. The idea that if you raise or lower a clock in Earth's gravitational potential, then the higher the clock goes, the faster it ticks compared to a lower clock. This is a very weak effect. To kind of lowest order, it just scales with the acceleration due to gravity times the change in height divided by c squared. And unfortunately, c squared is a big number. I mean, maybe fortunately for other reasons, but bad for this, right? And so what that means is that for a 1 meter height difference, you get an effect at the 10 to the minus 16 level. So it's a very small effect, but it's an effect that we can measure now that these clocks have gotten so good. This was first observed using Mossbauer spectroscopy in the famous Pound-Rebka experiment, using a height difference of 22 meters. And that gives you a difference between the source and absorber at about the 2 times 10 to the minus 15 level. And so with Mossbauer spectroscopy, you can be sensitive to this. And then subsequently, clocks have kind of caught up. And now at this 10 to the minus 18 level, clocks have become sensitive to the redshift at 1 centimeter. So if you raise one of these clocks up a centimeter with respect to another, that's now an observable shift. This is actually a huge problem for clocks, because what it means is that if you want to compare two clocks at two different standards institutes that are hundreds of kilometers or thousands of kilometers from each other, you need to know their relative heights with respect to Earth's gravitational potential to better than 1 centimeter to make sense of the frequency measurement that you perform, and that's a real challenge. But of course, you can always view that as either a bug or a feature. We actually don't have any way to do those measurements at better than the kind of 1 centimeter level, which means these clocks are now the best way to do it. And so people have now turned this on its head and said, let's use portable clocks to actually measure Earth's gravity and to determine relative height differences with respect to each other. And this is a kind of growing field that I think is very exciting, and there's a lot of great work on that going on here in Europe. I'm excited about this, but I'm even more excited about the idea that now we have access to a way to do tests of relativity in the lab. And you could ask, why do tests of relativity? I kind of already hinted at it, but I think the big motivation is we have these two very successful theories of general relativity and quantum mechanics, and we just don't know how to reconcile them. And I think it's particularly interesting to try to find situations where maybe you can see effects of both quantum mechanics and relativity showing up in the same system, and to maybe see how they kind of interface and interact with each other. This is not necessarily quantum gravity exactly, but it's kind of trying to work towards seeing some version of that, and to just explore how these two things, that we don't know how to reconcile, really interact with each other. And one beautiful example of a theoretical proposal for how you might do an experiment like that is this nice experiment that was proposed in 2011. The idea is you take a clock, an atom that you can put in a superposition of two energy levels, and you also put it, in addition to being in an internal superposition, in an external matter wave superposition, and you put it at a superposition of two different heights. And when you do that now, you can imagine that these atoms are kind of, because they're in clock states, they're measuring the passage of proper time along both of these paths, and because of the gravitational redshift due to gravity here, the atom's kind of learning about which path it took. So if you try to interfere it with itself, if you just do an atom interferometry experiment and you recombine it at the end here, the atoms actually should kind of know for certain interrogation times which path they took, and you won't see any interference fringe anymore. You'll see a complete lack of visibility in the atom interferometer visibility fringe. And this is kind of telling you that somehow, the atom learned about which path it was taking because of relativity, and you're sort of seeing that actually, when you're in a superposition, you're actually in a superposition of experiencing two different proper times at the same time, which is kind of an interesting effect. And this is only theoretical. I'll come back to this at the very end. But so I think that really motivates this idea of let's push beyond where these clocks currently are to the level where A, we are very good at creating kind of spatial superpositions, and B, also push beyond the kind of current geodetic limit, the way that we can measure these potentials in other ways, down to, let's say, this 10 to the minus 20 level. I'm kind of picking 10 to the minus 20 somewhat arbitrarily, but I think it's sort of well motivated. It's about 2 orders of magnitude better than clocks currently are. So that was kind of one of the goals that I set out with when we started building this experiment. So we built the strontium optical lattice clock in my lab. This is a picture of it. Here's the mott of strontium right there. And we bought a commercial clock laser from Menlo Systems. Here it is. Okay, we have this nice atoms trapped in our optical lattice. There's a picture of them. And we can do our experiment. And when we do it, we get a pretty good coherence time for an optical transition of about 100 milliseconds or so. And this is pretty good. And then you can plug in from that basic equation that I showed you and say, how good will this clock be in terms of this fractional frequency uncertainty? And our QPN limit here, naively, if you plug in kind of reasonable numbers, is something like 4 times 10 to the minus 16 per root hertz. Okay, so if I average for 1 second, then I'll have a fractional frequency uncertainty of 4 times 10 to the minus 16. Great, that means it will take 51 years to average down to 10 to the minus 20. Unfortunately, that's a bit longer than your typical PhD, and so I'm not able to convince my students to do this experiment. And this might be where this crowd would suggest maybe you can use entangled states to push past this, but unfortunately, the situation is actually that we're not even at this QPN limit, and because we're not limited by the quantum projection noise, we can't take advantage of these entangled states. Yeah, thank you. And so in fact, we are limited by something else which is called the Dick effect. It's basically a result of the fact that we have to stop our measurements to reload our atoms. Every time we measure them, we destroy them, and we have to cool and trap new atoms. And because of that dead time in our measurement, we end up aliasing higher frequency noise on our clock laser down into lower frequencies. And that means that actually the performance of our clock isn't limited by the number of atoms we have. And so using entangled states or something wouldn't help. And it also means that our clock is much worse than I told you from this simple expression. It's actually more at the 1 times 10 to the minus 14 per root hertz level. And that means it would take 46,000 years to average down to 10 to the minus 20. That's even longer than like tenure will allow me to keep running my lab, right? So we need to do something else. And so of course, we have a solution to that. And the solution is to do differential comparisons between clocks and to make this laser noise common mode. So the way that we do that is by loading multiple ensembles of strontium into one optical lattice and probing them with the same clock laser simultaneously. And these are actual camera images showing how this kind of procedure works. You can see that we've kind of loaded 2 different regions of our lattice. We do this by converting our standing wave into a running wave, kind of moving walkway style or conveyor belt style lattice. And we end up with 2 ensembles. And now if we probe one of them for a very long time, we do a Ramsey sequence and probe for well beyond this 100 millisecond coherence time of our laser, you can see we just get noise in terms of the excitation fraction of this. Just repeating the same experiment, we just get completely random outcomes every time. But now we have 2 regions, and so we can plot the 2 of them simultaneously, and we can plot them in a kind of smarter way. We can plot them parametrically, where we plot the outcome of one region on the x-axis, the outcome of the other region on the y-axis, and now you can see that these are forming this beautiful ellipse, and that's because we're just sampling 2 offset Ramsey fringes where the phase offset between them is determined by the detuning between these 2 ensembles, and that encodes, of course, the redshift and everything else that gives you a detuning, and then we're just randomly sampling it because our clock laser is doing whatever it wants from shot to shot, but we don't care. We do a lot of measurements, and then we fit to this ellipse, and we learn about the frequency difference without being limited by the performance of our local oscillator. So we can go from this 100 millisecond coherence time, doing this trick, to 26 seconds initially, and I'll show you we've even pushed beyond that, and that gives us a much better performance. That gives us a performance, so we can also now go out to beyond a minute of atomic coherence on an optical transition, which is really pretty astounding. And so that gives us stabilities of something like 7 times 10 to the minus 18 per root hertz now, which is orders of magnitude better than we had before for an absolute clock. And now if you look at the numbers, before it took us 46,000 years, now it'll take us 6 days to average down to 10 minus 20. And that's within the standard PhD range, right? So we're in good shape. And now also I'll mention, we are truly QPN limited. If you look at this plot here, you can see that actually we're averaging down right at the QPN is this dashed line. And so what that means is that you could take advantage of entanglement and things like that. So now we're back in a regime where using these highly entangled states really would help. Okay, so I'm running out of time, but very quickly I want to tell you, we actually use this to measure the redshift. And we play an additional trick where we actually don't just load 2 ensembles, but as many as we want. So here I'm showing us loading 6 ensembles at once. And that gives us kind of a vertical array of these ensembles where we're learning both about the redshift at 1 centimeter between this one and this one, but also simultaneously we're doing 4 measurements of ensembles separated in height by 2.5 millimeters. So we're getting a lot of different information about different redshifts simultaneously. So far I've only told you about statistical uncertainty, but we also have to worry about systematics. We have to worry about all the things that could mimic a redshift, like magnetic field gradients, electric field gradients, thermal gradients. We characterize all these things. It was a lot of work. That's the hardest part of these kinds of precision measurements is characterizing all your systematics. But we did it, and we actually did it blind so that we wouldn't bias ourselves towards getting the answer that we expect. And so here's the measurement as it was coming in, and this green region is the kind of range of possible blinds that our software might have been applying, and this black line is what we expect from the redshift, and you can see we're actually measuring the redshift with the opposite sign, but that's okay because of the blind. And when we finally decided we were done and we finalized our systematic evaluation and everything and we unblinded, we were very happy to see that it agrees. And so, big surprise, Einstein was right yet again. But in fact, we do see the redshift at the kind of centimeter and millimeter scale. This is my favorite plot of the whole thing, so I'll wrap up very soon, but just to show you, here you can actually see the redshift showing up across this array of atoms as a function of height difference. And we're really sensitive to the redshift at, a millimeter or so. So at the thickness of a penny, or since I'm in Europe, like 1 euro cent, or what, I don't know what you call it. But so this means that when you put your coin down on your desk and you leave it there, the top is aging slightly faster than the bottom. And if that bothers you, just flip them over every now and then. So I think this bodes really well for geodesy. I'll mention that we actually moved this apparatus after doing this experiment from Wisconsin all the way to California, so thousands of miles, and we now have it up and running again in our new lab, so it's kind of a portable clock, but I don't plan to ever move it again, so it's not very portable. And the last thing I'll say is that, okay, first of all, there were very nice measurements, similar and very complementary measurements from Jun Yi's group, but we're planning on kind of pushing on this, and one thing you can say is, can you really set competitive limits on modifications to relativity? And I think the answer is yes. We can measure the redshift at the millimeter scale, but we're kind of handicapping ourselves if we want to constrain modifications to relativity. We should really do it at larger height differences. So we're building a second generation apparatus with meter scale separations in height. I'm very excited about this. I think that we can actually set kind of competitive limits on modifications to relativity in the lab using this apparatus, as well as do some other fun searches for dark matter and things like that. And so I just want to skip ahead a few slides to acknowledge the people who did all this work. Here they are, and I'll just say we're having a lot of fun in my group, I think, and I'm always looking for talented grad students and postdocs, so if you're interested, come talk to me, and thanks a lot for your attention.
Thank you for this wonderful talk and also for staying on time. We have time for questions. Who wants to ask the first question?
Thank you very much. Beautiful experiments. I really like to see that. I have one rather technical question. In your Ramsey experiment with 8 seconds waiting time, you said it averages, essentially, it is random, but the contrast was still essentially 1. So why is that?
Yeah, that's exactly right. That's kind of the key insight, right? Which is that where all that noise is coming from is the laser. The laser is just randomly varying in frequency, which means the phase of the second pi/2 pulse is completely random from shot to shot, but the atoms are still coherent. And so that means that the contrast of the Ramsey fringe is very close to 100%. But you can't get meaningful information from trying to measure it with a laser where you have no idea what the laser did. You've just completely lost track of it. It's gone many, many pi of phase every single time in some random direction, right? And so that's why we can do these differential comparisons. If the contrast was really falling because the atoms were decohering with respect to each other, then you couldn't do this. And actually, just to show you an example of that, it's a very insightful question, so thank you for it. When we first did this and first tried these differential comparisons with these ellipses, I'll show you what we saw. We saw this, okay? And you can see that we went from 100 milliseconds to initially 6 seconds, and instead of having an exponential decay, it has a kind of Gaussian envelope. And initially I was very happy about this because we went from 100 milliseconds to 6 seconds, and then I started complaining, like, wait a minute, to my postdoc and grad students, like, why isn't it better? Like, what's limiting us, right? And it turned out that actually we were limited by a magnetic field gradient in our apparatus, and that was causing the atoms at the top of one ensemble to get out of phase with respect to the atoms at the bottom of one ensemble, so just across the spatial extent of a similar ensemble. So all we did was actually switch to a different transition that was less magnetically sensitive, different hyperfine states in the excited and ground state. And as a result, that allowed us to go from 6 seconds to 26 seconds. And it's just because we made the differential magnetic moment was 20 times weaker, and we were no longer limited by that dephasing. So that's an example where the contrast is actually going down. And otherwise, it's just this kind of random noise from the laser itself. Yeah, very good question.
Thank you very much. Yeah, thank you.
Do we have a second question from the audience?
Nice catch.
Yeah, beautiful results.
Thank you.
Seeing this progress, will this have some impact on the National Institute of Standards in defining the second And the other question is there another transition inside at even a higher frequency?
Okay, great questions. So one thing I want to emphasize is that you can't use this as a clock because we're only making differential measurements. You know, we're not, in a standard atomic clock, it's actually the laser or the local oscillator that's the actual clock. And we're now completely insensitive when we do these differential comparisons to what that laser is doing. So you can't use this to redefine the second or something but it can still be helpful. For example, you can use it to characterize systematics. And we've already started doing that. You know, these clocks, one of the things that limits them or the primary thing that limits them is kind of understanding all of the systematic shifts that they're subject to. And now by doing these differential comparisons, you can learn about all of those much faster and also do things like measure gradients inside of your chamber. And so I would say more and more groups are actually starting to adopt this. There's also related tricks that I didn't talk about, but we have a paper about, where you can actually use multiple ensembles in a different way to actually make a better absolute clock, and I do think that can help. And then your other question is there a different transition? In strontium, I would say this is the best transition. There are higher energy transitions and other transitions, but they're more magnetically sensitive, for example. So this is probably the best transition in strontium, but of course you can move to another element, or you could maybe even move from an electronic transition to a nuclear transition, and that's this very exciting recent developments with the thorium nuclear clock that I think is really exciting, but probably won't contribute to the redefinition of the second anytime soon. I think before that, we will switch to one of these optical standards or some combination of these optical standards, you know, in 10 years or something like that, once we have all the ratios under control and everything looks good. Yeah.
Perfect.
So in view of time, I think we have to move on. So, Thomas, please, let's thank the speaker again.